Okay, let's compute an arc length. So I have this curve, f of x equals 1/2 x to the 3 halves, and I'm interested in the length of that curve on the interval 2 to 3, so I shaded that part of the curve in yellow on the graph. And this is our arc length formula, and if you're curious where that came from, I'll link back to a video of a short derivation that I did just to clarify where that came from. So it looks like we have to compute f prime of x. And just running through the math real quick, I end up with 3/4 square root x, and when I square that, I end up with 9/16 x, and then I can get into my arc length integral. So s equals the integral from 2 to 3 square root 1 plus 9/16 x dx. So on this integral, if you like, you could do an explicit substitution where you let u equal the interior of the square root, and then du would be 9/16 dx, and so on. My preference is to be less formal than that, and to just build the derivative of this interior out here in the integrand. So all I need is a 9/16 for that. All right, so now I see the square root of a thing sitting right next to the derivative of that thing, and I can see how to do the chain rule backwards. So you can't just go around multiplying things by 9/16. You have to make up for it by multiplying by 16/9. So that's legal now. And this is just something to the 1/2 power. And when I integrate it, I get that thing to the 3/2 power. So all this stuff I'm saying is really, it's equivalent to doing an explicit u substitution, but when you start applying calculus at the next level, you want to be efficient like this at building the chain rule backwards. So I get this thing to the 3/2 divided by 3/2. In other words, 2/3. That's 1 plus 9/16 x to the 3/2. And then I'm evaluating x from 2 to 3. All right, so I don't see anything I can cancel out here, so I'm just going to write this as 32/27 out in front. And then in my upper limit, I plug in the 3 here for x, not for 9, but for x. And I end up with a 27/16, so I have 1 plus 27/16 to the 3/2 minus what I get when I plug in 2 for x, which would be 18/16, so 1 plus 18/16 to the 3/2. And there's not a heck of a lot you can do with this. You could get a common denominator in here. And that would be 16/16 plus 27/16, which I think is 43/16 to the 3/2. And then this one would be 34/16 to the 3/2. And you could actually play around with those denominators a little bit, but at this point I'm just going to get a decimal approximation. And when I did it, I got something like 1.55 units for the arc length. And if I look at my graph, each one of these grid squares is 1 unit, so you should check to make sure it looks plausible. If I tilted that grid square, it would go from about there to there. And so the idea that there's 1.5 grid squares worth of length in that arc is at least plausible.